Coulomb's law provides a way for us to calculate the electric force between two electrically charged particles. And so we have this equation here. The force between two particles or charges 1 and 2 is equal to 1 over 4 pi epsilon naught times Q1 times Q2, and these are in absolute value, divided by r squared. The r is the distance between the two charges. If these charges have the same sign, the force is in the same direction as r, and this shows a repelling force, as so, right down here. And if the charges have different signs or opposite signs, the force is in the opposite direction of r, showing an attractive force, like down here. Okay. I should also mention a couple of these terms here. The permittivity of free space, or the permittivity of vacuum, is epsilon naught, and that is equal to 8.85 times 10 to the negative 12th Coulomb squared over Newton meters squared. And this is a constant. Then we also have Coulomb's constant. That is going to be 1 over 4 pi epsilon naught, which comes out to 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. Okay, so these are just a couple of constants that we will be using, so you may see these sprinkled in. All right, so if we don't just have two charges, but we will possibly have multiple source of charges, and so we have to come or think about the principle of superposition, where we can add up all the forces due to the charges acting on one single object or one single charge. So in this case, this charge is Q, and the force, the electric force on this charge will be this constant, 1 over 4 pi epsilon naught, times the charge Q, capital Q, times the summation over all the Q's, Q sub I over divided by R sub I squared, and then R hat I gives our direction. So this piece right here is telling you at each Q, so Q2, 3, 4, 1, 5, all the way through 8 for this example in particular, will be included in this summation, okay? And all of their distances. So their distances from that one charge, that specific charge, Q, capital Q. And so that would be R2, 3, 1, 4, 5, blah, 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 continued all the way to R8. Okay, so this would be the sum of all of them. We should note that Qi are the in-source charges, so however many there are. Like we said here, there's one all the way through 8. And then our vectors, R hat, are the displacements from the position of the ith charge of the position Q. So this would be the displacement for Q1, and then the displacement for Q2, and so forth. Q, capital Q, represents the charge of the particle that is experiencing the electric force, and it's located at some distance r from the origin. So if we have some origin, say here, this would be the distance from that origin. Okay. Now we need to talk about the concept of a field. What the heck is a field? It is basically a way to look at or conceptualize the force that surrounds any object and acts on another object at some distance without an apparent physical connection. So let's take, for example, if we have N sources, capital N sources, located at some positions, applying a number of, or N, electrostatic forces on a test charge, capital Q. So we have some capital Q, and the net force on that test charge will then be force F is equal to Q times E, What is this E? This is our electric field. E is going to be our electric field. So our electric field at any point P, which in this diagram here would be here, point P. So the electric field at that particular point is equal to, or defined as, 1 over 4 pi epsilon naught times the summation of Qi divided by Ri squared, and this is giving our direction r hat sub I. Okay, so we have not just one electric field at this point, we have a summation of fields that are acting at this point on this test charge, Q. Okay, so we have Q1, 2, 3, 4, 5. All of these are acting on this one point. So we need to, again, talk about fields because that was a very brief overview. But we need to know a couple of things, that the electric field is a vector quantity. Okay, so as we saw in the last slide, E had the arrow on top of it. So that means it is a vector quantity. So it is referred to as a vector field. So an electric field is a vector field. Now, a field that only has magnitude at every point is a scalar field. Okay, we're not going to deal with those right now. We are focusing on vector fields, but just kind of note that they do exist. Now, the direction of this vector field, we, by convention, say that all electric fields E point away from the positive source charges and point toward the negative source charges. And we will get a little bit more into that in a little bit when we start drawing these out. But just know that the positive charges will point toward the negative charges. So with that, we need to also talk about real life applications of this. So far we've seen point charges, we've seen just point particles that have some charge to them. But there are also things that have a continuous distribution of charge. So like the rods that we were seeing, or something, what was that, like a cloth. These are continuous charge distributions that have at least one non-zero dimension, meaning it has maybe 2 dimensions, 1 dimension, 3 dimensions. And with that, we need to define a charge density for the charge distribution along a line, across a surface, or within a volume. So with each of those, we need to define some sort of charge density in order to find what these electric fields are for these cases. So here in part A, we have a line charge. So this would be like an infinite rod, say. So an infinite rod would be just a line of charge. Then we have a surface of charge, and this would be maybe like a very, very thin sheet of paper. That would be a good example. And then we also have a volume, which would be any sort of volume. Oops. Okay. So again, we have linear charge density, which is going to be represented with the Greek letter lambda. So this is charge per unit length. So this will have units of coulombs per meter. Okay, so again, charge per unit length. Then we have surface charge density, and that is represented with sigma. And sigma is going to be the charge per unit area, or our units will be C, or coulomb, per meter squared. Then we have volume charge density, which is going to be represented by rho. That's not a fancy P, that is a rho. Okay, RHO, and that is going to be the charge per unit volume with units of coulombs per meters cubed. Okay, so that's the basic idea of these charge densities. This is how we define them. Now we need to find the electric field for each of these. So again, we have defined it for a point charge. So this is the equation for a point charge. So at a certain point in space, this is what our electric field will be. What about for a line charge? Well, for a line charge, we will now need to um, go up to something, not just a summation, now we need to take an integral. So we will have the same constants out front, 1 over 4 pi epsilon naught, that doesn't change. And then we take the integral over the line of the lambda, which is our density, dl, which is our length, divided by r squared, and this is r hat, that's our direction, okay? It's our unit vector direction. So we have lambda dl over r squared. For surface charges, we have something very, very similar. Again, we have our density, our surface charge density, times dA, which is our area. So we're taking the integral over the area, divided by r squared, r hat. And then for volume, we have, again, something very similar, where we have rho d volume over r squared. We're taking our integral over the volume, and again, direction. So we need to note the meaning of r in each equation, which is the distance from the charge to the location of interest. So from the charge Q, or whatever it may be, to the location of interest, okay? Then we also need to note the meaning of r hat in each of these equations. So for example, if we're looking specifically at the line charges, we would actually break that up into the x direction, y, and z direction. So E bar, or our electric field, would have an x component, y component, z component, 3 dimensions, and then we'd have the same equation for each of them, but each of them will have a different direction, so the x, y, and z directions. So maybe the electric field is purely in the x, or maybe it's a little bit in the x and in the z, or so forth, okay? So this is how we will be able to break that down. All right, so let's take some simplified cases. So first, let's look at for a finite line of charge where z, the z component, is much greater than L. So whatever L is, so z squared dominates the L in the denominator. So we obtain this equation here. Okay, so this is from, we go back, this is from this equation or this equation, however you want to look at it, okay? So we're integrating over our L, our line, so L would be the length of our finite charge, our finite line of charge, I should say, and then z squared is going to dominate it. So as we take a limit, as L goes to infinity, okay, we get the field of an infinite straight wire. So sometimes we may ask, what is the electric field of an infinite straight wire? This is the equation that we will use. So the electric field in one dimension, let's say z, is going to be 1 over 4 pi epsilon naught times 2 lambda over z, okay? Again, z is that distance, right? If we go back, that meaning is going to be the distance from the charge to the location of interest, okay? And we will look at examples in person. I think that'll be a lot easier for us to do. All right, so what about for an infinite plane? Say we have an infinite plane instead of an infinite straight wire. So as r goes to infinity now, we obtain a flat sheet whose area is much greater than its thickness. So something like a really, really big sheet of paper. The sheet of paper is still really, really thin. It's extremely thin compared to the area of the sheet itself. So we obtain a oh, this should be, okay, well, this is the electric field on that flat sheet, and that will equal uh, sigma divided by 2 epsilon naught times k hat. So k hat, again, giving us the direction. Okay. All right, so let's look at electric field lines. And again, these are used to visualize field strength and direction. So very much like vectors. These are like vectors, but now putting them into a little more context, and there's more lines involved here. So we can look at, let's look at this image first. Okay, so we have a electric field uh, electric field lines, and it's showing we have larger, or larger arrows here, right? The arrows are bigger. Okay, so this tells us, or indicates to us, that the field strength around whatever this middle object is larger than if we start to look out here. We've got really small arrows. There are still arrows there, right? They're still present, but they are much smaller. So the electric field in this area is much greater than out here, as we have a greater distance. So this is very similar to, when we're looking at gravity, right? We just looked, or no, we didn't just look, but last semester we looked at gravity, and the strength of gravity has that 1 over r squared component. It's very similar, right? We have the electric field gets weaker as we go away, just like the strength of a gravitational field, okay? And we can also look at this in 3 dimensions. So this is 2 dimensions. If we go over to 3 dimensions here, same idea. We have the larger arrows, or larger vectors, towards the center here where the charge is, versus as we go out, they get smaller. So the electric field is weaker on the outside, okay? All right, we can also visualize this in a very basic way, I would say. Say if we just have a positive charge here, we will have electric field lines that are pointing away, right? Because positive to negative. That's what we said that the flow goes from. It goes from the positive charges to the negative charges. And if we look at a negative, it's going to be the same. We have the same number of field lines, but this time they are attracting. We have an attractive force here. So the electric field lines are coming towards. If we have a charge that is twice the amount of this negative charge here, so we have, like, say 2 or 3 times this charge, we have more electric field lines. So this is another way that we can represent this, more electric field lines, okay? All right, we can also talk about field line density, which is going to be the number of field lines per unit area that passes through a small cross-sectional area that's perpendicular to the electric field. So in this instance, we have some amount crossing through this cross-sectional area, right? At another point, we may have more or less, depending on what's going on with the electric field. So it seems like, just, looking with our eye, what the heck, sorry, just looking, we can kind of tell that this isn't as dense of a field here, right? The lines aren't as close together, they're further apart. Versus here, they look like they're much closer together. So this is kind of like also B here versus C. These have a lot more closer together, and this one are more spread out. But this is, of course, due to the field strength, okay? All right, so let's move on to actually drawing these guys. Now, they, like I said, begin on positive charges and end or terminate on negative charges, or at infinity if you're in a hypothetical case of isolated charges. Um, and the number of field lines leaving or a positive charge or entering a negative charge is proportional to the magnitude of the charge. So again, more or less depending on how strong that charge is, the magnitude of the charge. At every point in space, the field vector at that point is tangent to the field line at the same point. The strength of the field is proportional to the closeness of the field lines, and field lines can never cross. So keeping some rules in mind, and we'll get some practice with this as well. But we can have two charges closely together and then draw what the field lines will look like. So just to kind of get some sort of idea of what's going on between the charges. So say, for example, in A, we have a positive charge and a negative charge. So the positive charge will go towards the negative charge, right? That's what these arrows are doing. And they kind of do this thing where they just keep reaching out until they can't really connect anymore. Okay, so this would be the attraction between these two charges, a positive and a negative. Now, we can also have another way to depict this here. This one actually, I think, I didn't write down the description, unfortunately, but I believe that this positive charge has more magnitude to it, so it can't connect all of their field lines together. So it starts to kind of branch out, reach out for any other charges in the area, basically. Okay, so that's what this would look like. This is more magnitude over here. Then if we have like charges, say positive, positive, or negative, negative, we will have this repelling um, uh, field lines here, these repelling field lines. So the positive is going to, go down or go up, and same thing on the other side, but they'll never touch, they'll never cross, okay? All right, so I think I'm going to pause here, and then we'll continue.